Hello guys, welcome back to our channel. Today we are going to see how to make the Vella code for the logic gates for data flow modeling. In the previous video, we completed the Vella code for the different logic gates using the gate level modeling. As we know that there are three different styles of Vella modeling. There are gate or structure level modeling, and next one is the data flow, and next one is the behavioral modeling. Out of three, data flow modeling, today we are going to see how to make the Vella code for the different logic gates. So let's start the Vella code for making these logic gates using the data flow modeling. So for that, I'm creating a module with the name called logic gates. As we know that there are seven logic gates which are available. I mean, out of those, three are basic gates, two are universal gates, and two are the special gates. So for that, I'm taking inputs, two inputs, one A comma B, and outputs I will take 7 because we have 7 gates to perform the operations. One is OR gate, and for OR, and for NOT, and for NAND, NOR, XOR, and finally XNOR. These are the different 7 gates which are available in the digital electronics. And now after taking this, we will, in the data flow modeling, we have to assign the operation to the output. That is, assign is the keyword. And for the AND operation, we know that AND is nothing but the multiplication of the A and the B. That means the addition of the two inputs, so A into B. And for the OR, the addition between the two inputs. And for the NOT, the one input will be complement to the output. That is, I will take A. And for the NAND, it is nothing but just applying a complement to the AND gate. So complement A into B, and NOR is nothing but the applying the complement to the OR operation. OR is nothing but the addition of the two inputs. And for the XOR, we know that the expression for the XOR is AB bar plus A bar B. So A bar B, I mean A into B bar plus A bar B. And simply XNOR is nothing but just applying the complement to the XOR gate. So I'm just copying the XOR value, and I'm pasting it, and I'm applying a complement. So these are the all the 7 logic gates which are available in the digital electronics, and I am ending this design code with the help of a syntax called end module. Okay, now this is the design code for our 7 logic gates for using the data flow modeling. Now we will create the test bench for this logic gates to verify the operation whether they are performing good or not, I mean correct or not. So for that, I'm creating the module with the name called TB. TB is nothing but the test bench, and here the inputs will be considered as a register A comma B, and the outputs will be considered as the wire. These are the outputs. I'm just copying from the design code, and I will be pasting it in the test bench. Yes, okay. Now for to perform the logic gates, I am taking this logic gates and logic gates 1, and we have to write all the inputs and outputs within the this parentheses: A comma B comma and comma R comma not and no, XOR, and finally XOR. These are the inputs and the outputs for our logic gates, and we will start this process by the command initial begin, and I will use the dump file command, which will be used to obtain the graph file to verify the functionality of the different logic gates. And I'm saving this file with a file name called file.vcd. And properly see the indentation. It is more important while writing the verilog code. Compares one. and we have two inputs, that is a and b, and two inputs means we have 2 power n, that means 2 power 2. When we will get 2 power 4, I mean 2 power 2, 4 combinations of inputs we will get. So first a equals 0, b equal to 0, and I'm taking as hash 5, that means the hash 5 is nothing but the delay for the one input to the next input. And a equal to 0, a equal to 1, sorry, b, hash 5, a equal to 1, b equal to 0, hash 5, I mean hash 5 is nothing but the time delay, and b equal to 1. And after giving all these inputs, I will finish this test bench by using the command hash finish, I mean dollar finish, and end, and finally end module. This is the test bench code for our design code. Now we will execute this Verilog code whether it is working good or not. So for that, in the tools and the simulators, select the, you can select any one of these. I am selecting the IQRS Verilog 0.9.7. Through this we can see the graph of the code, and I'm selecting the open EPV after run, and I'm saving. Now I'm going to run this code, whether it will be good, I mean whether it will be working good or not. Yeah, we have to give the name for this. I'm giving the name called logic gates, using, we have write this code using dataflow, right? So I'm giving the logic gates using dataflow modeling. Okay, right, we will save this file, and I'm going to run this. If you have any errors, sorry. Okay, now I'm going to run this file by pressing the run command. Yes, the program is running. As this is the output file for our code. Here you can see that initially the a and the b values are 0. So the and is nothing but the multiplication of the a and b. So the value is 0. NAND is complement of the and. The and value, the and output value is 0, and the NAND output value is logic 1. And these are the output for our logic gates using the data flow modeling. And thank you for watching this video. Stay tuned for the next video.